here we have this is Bcd textbook. So that is the PPT of the Bcd textbook. Uh, so arithmetic and logic instructions and programs. So we are going to deal with some instructions. First one is add. So you know that add is add a comma source. So when you're using the operator add, that it should be add a comma a register. It can also be a particular value, that is you can use immediate addressing also. So what is done is the accumulator will get the value in accumulator plus whatever is stored here. Okay, so that is the case with add. So it will be used to add two operands, and the destination operand is always the accumulator. The source operand can be a register, immediate data, or memory. Okay, so here we can see that we are going to add two numbers, 0F5H and 0BH. So this is the addition. So this is hex addition. So you can either do it in hex or you can convert it to binary and add. So the result which you are getting is 0000 with a carry 1. Okay, so here since the carry is 1, there will be a carry out from D7. This is D7, the MSB. So there is a carry out from D7. That's why you have an additional bit here. Okay. So PF is the parity. So PF is equal to 1 because the number of ones is 0. That is an even number. So the parity flag is set to 1. AC is the auxiliary carry, that is from this position. D3 to D4 is there a carryover. Uh, so here 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1. So from this particular location to this location there is a carryover. So there is an auxiliary carry also. So this is just to tell you how the flags are set. Carry flag in the PSW, you have the carry flag, you have the parity flag, you have the auxiliary carry flag. So what is the result of the PSW, each bits in the PSW after an addition operation. So this just gives that example. Since here you have a carry CYS1, here you don't have any ones, so 0 ones, so the parity flag will be 1, and since there is a carryover from D3 to D4, auxiliary carry will be equal to 1. Okay, so that is how the addition is done. This we will deal with in EdSim. So next is adding two 16-bit data operands. 16-bit data, the earlier case was 8-bit. Here we are dealing with 16 bits, that is 2-byte data. So here you have 2 bytes of data. You're going to add two 16-bit numbers. So here 7 plus D is done, then E plus 8 is done, then C plus B is done, 3 plus 3 is done, and if there is any carryover, that should also be considered. Okay, so when the first byte is added, that is first byte is the lower byte E7 and 8D, that is added. I'm getting 74. There is a carry 1. If I'm adding just this, okay, I'm treating it as a 16-bit number. I'm treating it as two 8-bit numbers. So first I'm going to add just E7 and 8D, and I'm going to get a result there. And here, when you do just this, you have a carryover. So that's why I'm saying that here there is a carry. That carry is propagated to the higher byte. That is, that carry will come here, and that will be added with 3C and 3B to get 78. So that is the logic of a 16-bit addition. So in the case of 8-bit addition, the result will be in 8 bits. So if there is a carry, then that is if you are adding many numbers, not just two numbers. If you are adding many numbers, the higher order byte will be incremented every time a carry occurs. Okay, so if a carry occurs once, the higher order byte will be 1. If a carry occurs twice, that will be 2, 3, it will be 3, like that. The lower order byte will give you the correct answer. Higher order byte will give you the incremented, how many times the carry occurs, that value. So that is add in 8-bit data, and the 16-bit addition. In 16-bit addition, we'll be using add with carry. Add with carry to do this particular operation. So that will deal in XM, these two problems. So next is BCD. So in BCD, we know that we have a value. Each decimal digit is represented using 4 bits for a BCD. So 0 to 9 can be represented using 4 bits in BCD. If there is if there are two digits, then you need 8 bits to represent that. And we have also studied in the earlier semester that if it is not a valid BCD code, then you add 6 to that number to get the valid BCD code. So for that, we have a operator. Okay, so this is an example. You are going to add 17 and 28. So 17 plus 28 should be actually 45, but then you'll be getting, when you add these two hex numbers, you'll be getting 3F and not 45. So in order to get 45, because 3F is not a BCD number, because F is not a BCD number. BCD number can be only till 9, 0 to 9. So F is not a BCD number. So you know that this is not a valid BCD code. You have to add 6 to that particular digit. So 3F should be added with 6 to get 45. So for that, you have a operator called DAA, decimal adjust for addition. So this is specifically used for BCD addition. So you have these two values. A gets the value 47 and B gets the value 25. You're going to add these two numbers. So by the look of it, you know that you won't be getting a valid BCD code. You'll be getting 6C as the result, where C is not a valid BCD code. So you know that the result is not valid BCD code. So you'll be adding 6 to it. So in order to add 6 to it, you needn't specifically add 6 to that number. You just need to give A is the accumulator. This A is the accumulator. So the result, the BCD, the addition sum should be stored in the accumulator so as to give this particular operator. Okay. So here the result is in A. So decimal adjust A means 6C will be added with 606 to get the value 72, which is the actual result. Okay, so DA will work only on the accumulator. So you should have the sum in the accumulator, only then you can use this particular operation instruction. Okay, so that is DA. So this is an example, 29 plus 18. Your result is 41. So you know that the actual result is not 41, it is 47. So in order to get that, you need to add 6 to it, so that you get the value 4 and 7. Okay. The final result is in the BCD format. So here there may be a confusion that this 4 and 1 both are valid BCD numbers. So then why do you need to adjust? So this is 1. Why? This is 1, but there is a carryover here, right? So here 1 plus 1 is not actually 0. It is 0 with a carry 1. So this lower byte is not actually 0001. There is a carryover also. So it is a value higher than 1. Okay. So you know that what you are getting is not a valid BCD code in the lower byte. It is greater than what? Greater than 15. Okay. When we learned BCD, we had many conditions. One is it is a number greater than 9. It is a number between 0 and 9. That is valid. Next is it is between 9 and 15. That is not valid. The third case is it is a number greater than 15. So this is the third case, greater than 15. Okay. So in that particular case also you need to add 6. So in that BCD adder, we used to check the carry out, right? If the carry out is equal to 1, then you add 6. Or if the value is greater than 9, then you add 6. These are the two cases where you add 6. So this is the third case where there is a carry out. Where is the carry out? Here it is the auxiliary carry. D3 to D4 there is a carry. So that's why you are adding the 6 here to the lower order byte. Okay, so the next question is, assume that RAM locations 40 to 44H have the following values. sum of the values. So you have 5 bytes of data stored in location starting from 40 to 44H. And you have to take all these data and add them together. At the end of the program, register A should contain the low byte and R7 should contain the higher byte. Okay, so you're going to add these 5 bytes and the result will have 2 bytes. The higher byte will be in R7 and the lower byte will be in uh, register A should contain the lower byte and R7 will contain the higher byte. So these are the values. 40, the location 40 has the value 7D, 41 has 3EB, 42 has C5, 43 has 5B, 44 has 30. So these are the values in these locations. So you are going to access these locations and add the values stored there. Okay, so how do we write this? So we have to specify the starting address and we'll store it in some register. What is the starting address? It is 40. So how many bytes of data? So the data is stored in consecutive locations 40, 41, 42, 43, 44. So we'll store 40 in a register, then we'll store the counter, that is 5 bytes of data. So 5 is the counter that will be stored in another register and then we'll do the operation. Okay, so we can just move the value 40 to a register, say R0. Yes, then we can move the set the counter, move R2 comma hash 5. So then if there is any value in A, you can clear it. In XM, that won't be an issue. So if there is any value in it, it can be cleared. Now A should contain the lower byte and R7 will contain the higher byte. So you're going to store the result, the addition result, the sum in R7 and A. So first of all, I'm clearing A, which will be storing the final lower byte, and I need to clear R7 also. So for that, I'm just moving A to R7. So since A has a value 0 here, by clearing it, I'm just moving that 0 to R7. So R7 is also cleared. Okay. So next, we have to take the first data, that is 7D, from the location 40, which is pointed to by R0. Okay, so we'll use indexed programming so that we'll just add A with the content of 40. So how do we do that? At the rate R0. Yes. So content of R0. The content of R0 is 40 and content of 40 is 70. So 70 is added with A and the result is stored in A. That means that A now contains 0. So 0 plus 70, that is stored in A. So A has the first value. Yes. So when you add this, if there is no carry, then we will go to the next byte, say L2. So we'll be incrementing R0. And if there is a carry, then I'll be incrementing the higher byte, which is R7. Yes. So during addition, if there is a carry, then the higher order byte will be incremented. If there is no carry, then the lower order byte, then we'll take the next data and add to A. So increment R7 is only when there is a carry. So if there is no carry, then you're going to L2, that is you'll be getting the next data, and this will continue until all the 5 values are over. So that will be comma, say L1, where L1 is here. Right? So this will continue until R2 becomes equal to 0. What is R2? 5. So what is done? R0 first becomes 40, then R2 becomes 5, A and R7 is cleared, then A gets the value 70, so we'll just load these values 40, and we'll see 40 has the value 70, enter, so 40 gets the value 70, 41 gets the value EB, enter, 42 gets the value C5, 43 gets the value 5B, enter, 44 gets the value 30. So we have stored the values in 40, 41, 42, 43, 44. So that's the input. So we can check the value of R0. Here you have R0. So R0 will be 40 first, then 41, 42, 43, 44. Okay. At the end of the program, R0 will be 44. R2 will be 5. Then it will become 4, 3, 2, 1, 0. When it becomes 0, that's the end of the program. And R7 will be incremented each time when there is a carry in the addition, and the result, the lower byte will be stored in A and the higher byte will be stored in R7. Okay, so you can just save it and run the program. You can see R0, R5, R0 will be incrementing, R5 will be decrementing, sorry, R2 will be decrementing, and the final result will be in A and R7. Okay, so we will just run the program. So here you can see R0 is incrementing, R2 has decremented, and the final result is in accumulator. A is accumulator and in R7. So you can verify whether the answer is correct. So I'll just stop it and run it again and reset it, and you can check R0. R0 is incrementing, R2 is decrementing, R7 and accumulator value. Okay, so next we'll see another program, which is the 16-bit addition. So in that was the 8-bit addition, 1 byte addition. So this is the 16-bit addition. So here what you are going to do is add two 16-bit numbers and place the sum in R6. R6 should have the lower byte. So here we are going to define this 16-bit data. So for this you need the carry flag. So we'll just clear the carry flag first. So that is done using clear CLRC. That means clear the carry flag which is in the PSW. And I'm going to add, that is, I'm going to add the values 0E7, 0E7H plus 8DH. Suppose these are the two values I'm going to add. 0 is put only to notate that this is a hexadecimal number, since it is starting with the alphabet. I'm specifying it as 0E. So it is E7 plus 8DH. Okay. So that is the lower byte, and the upper byte is, that is, say, suppose the entire number is, say, 3C E7, and that is added with, say, 3B 8DH. So what will you do? E7 is added with 8D and 3C is added with 3B, and also you'll consider the carry coming from this lower byte addition to the upper byte. That is, when you add E7 and 8D, if there is a carryover to the higher order byte, that is, when you add 3B plus 3C, is there a carryover from the lower byte? So that is also considered. So I am clearing the carry flag. If there was any flag set before the execution of this program, that is cleared. So I'll be first adding the lower order bytes. So for that I'll have to keep it in a register. So I'll move one of the bytes, one of the lower order bytes to the accumulator. So move A comma 0 EH, sorry, E7H, and other I'm just adding, that is A now contains E7, so that is added with 8D. Okay, so this you can do only with accumulator. That is why I'm moving this to the E7 to the accumulator itself, because you can write it only as add A comma something. So that's why I moved the first byte to the accumulator itself. So now what is happening here? E7 plus 8D will happen, and that will be stored in accumulator. Okay, so that is the lower byte addition. Now the result should be stored in R6. The lower order byte result should be stored in R6. So here the addition has happened and the result is now in A. That should be moved to R6. So how will you move that? Move R6 comma A. So now E7 plus 8D, that result is in A and that has been moved to R6. So R6 contains the lower byte of the sum. Next we'll add the higher order bytes. So how will you add that? Move A comma hash. So what is that? 3C and 3B. So we'll take 3C first, then like in the earlier case. But here what you should do is you have to add with carry. Why add with carry? Because there can be a carry over from the lower byte. When you add E7 plus 8D, there is a chance that there is a carry from those lower order bit addition. So that carry should also be considered while you add the higher order byte. So for that you'll have to write add C. Okay, so if you write just as ADD, then that carry will not be considered. So in order to consider that carry, you have to write ADD C A comma the next byte, which is 3BH, and that result I'll move to R7. So where do I have that result? That is in accumulator. So I'll move that to R7. So the lower order byte is first added, that is moved to R6, and the higher order byte is added with the carry from the lower order byte, and that is added and moved to R7. Right? So okay, so here I need not store the value here. So I'll just save this and run. Okay, 3C. Okay, there is an error here. So 3C should be 3CH. Okay, so R6 and R7 should have the final result. R6 and R7 should have the final result, and R7, whatever is in R7, that should also be there in the accumulator. you can verify whether the answer is correct. So you can do this with any numbers. You can use indexed addressing also by storing these values in some location, and just using the register name to address those location, and thereby you can change the values. So in this particular case, it is just 3CE7 plus 3B8DH. So if you want to change, if you want to be more flexible, if you want to change the values, then you can just assign a particular location to a register like in the earlier case, and use indexed addressing to point to that particular location. Whatever is there in that location can be locations can be added in a similar fashion. So this is specific to a particular set of numbers, addition of two particular set of numbers. You can make it more flexible by using indexed addressing. Okay. So that is the case with 16-bit addition, and the earlier was 8-bit addition.